Hello, everyone, and thank you for joining Armstrong Fluid Technology webinar series. My name is Gloria Lee, and I am your moderator for today's session. If you are a first-time attendee, welcome to our webinar today. And I also see a lot of regular audience too, so welcome back. Today's session is quite special. Joining us today is Ramon Guitart, the VP of Application Engineering at Infinitum, and he will be presenting part 2 of Become a Pump Motor Expert in 30 minutes. Ramon brings over 35 years of expertise in electric motor and inverter development. Throughout his career, Ramon has held key technical leadership roles at renowned companies such as GE, Westinghouse, Rockwell Automation, and Trane, where he led teams in advancing and cutting-edge motor technology. He earned his Bachelor of Science in Electrical Engineering from the University of Wisconsin-Milwaukee and his Master of Science in Engineering from Marshall University. When he's not focused on advancing motor technology, Ramon and his wife enjoy traveling across the country to visit their 6 children and many grandchildren, spending in church time with his family. At the end of our presentation, we will have a Q&A session. Joining us is Nick Chui, Offering Operation Manager for Pumps at Armstrong. To ask a question, please type your question via the questions icon located at the top right-hand corner of your GoToWebinar screen. If you're experiencing audio issues during the session, we recommend you log out and log back in. I would now like to hand over today's session to Ramon.
Thank you very much, Gloria, and welcome everybody. Good morning to some of you, good afternoon to some of you. I really appreciate you spending some time with us, and we'll try to make this worthwhile for you to become motor experts in the next 25 to 30 minutes. The agenda for today will be a quick recap of the part 1. We will talk about some advances in motor technology, and then we'll discuss some future trends in pump motors. At the end, as Gloria said, we'll open up to some questions and answers. With that, let's recap part 1 of this webinar. In the picture, you see the classic induction motor in modern days. This motor is composed of 2 main components. One is the stator, and second is the rotor. The stator is a set of windings. Basically, in most motors, it'll be a 3-phase winding. And these windings are separate and independent sets of coils that are put together in such a way that they form poles. This winding, when connected to a 3-phase AC power supply, will develop a magnetic field. This magnetic field will rotate around the stator at a very specific speed. That speed is known as synchronous speed and is normally calculated by a specific formula. The formula is equals to 120 times the frequency divided by the number of poles. So if we apply that formula to a 4-pole motor that is connected to a 60 hertz power supply, then the field speed will be equals to 120 times 60 divided by 4, or 1800 RPM. In most cases, the stator has maybe up to or more than 6 different components. You have the copper wire, you have the insulation of that copper wire, you have insulation between the copper wire and the stator core. The core will be electrical steel. You will have lacing material to keep the stator away from the bore. And eventually you put it all together with varnish. I want you to make a mental note of that, and that there is at least 6 components to make a normal classic stator for an induction motor. The other main component is the rotor. The rotor also has windings, but they are very different from the ones that we talked about in the stator. The windings on the rotor are basically aluminum bars, they're cast, and they are short-circuited at the end by 2 aluminum cast rings. So this Rotor is a short-circuited winding. So in essence, when you look at a very simplistic way, the induction motor can be thought of as a transformer, where the main winding is the primary and the stator, and the secondary is the winding on the rotor. And for that particular reason, some induction motors sometimes will make the humming noise that is related to frequency. When we talk about the rotor, we also need to know that if we apply power to the stator, that magnetic field developed in the stator will exert a power onto the rotor. But because the rotor is mounted on bearings, it will tend to rotate. And it will rotate at a speed usually lower than the speed of the magnetic field. At full load, for instance, in a four-pole motor, the rotor will rotate around 1750 RPM. If you recall, the field is rotating at 1800 RPM, but the rotor is rotating at 1750. That difference of 50 RPM is known as the slip. And the slip is a very interesting concept that we're going to leave for webinar 103. But let it suffice to say that the slip is responsible for the torque developed by the motor at different loads. Let me now take you to a younger motor. This motor is the PN motor, sometimes known as the EC or electrically commutator motor. And this technology is about 60 years old. It came about when the transistor was discovered to be a very fast switch. From the picture on the right, you will see that the PN motor and the induction motor have a lot in common, particularly the stator. The stator on a permanent magnet motor is exactly identical to the stator on an induction motor. The main difference is the rotors. If you recall, we have a short circuit winding on the rotor for the induction motor. However, on the PM motor, now you have permanent energized magnet. And the permanent obviously is what gives the name to this particular motor. Some of the rotors are laminated and they have slots where you position the rotors, the rotor magnets. For that reason, this motor is also known as a synchronous motor. Okay? The magnets are now real. They will form poles of their own. And that's opposite to what induction motor. In the induction motor, the rotor creates or only the number of poles that the stator tells them to have. But in the PN motor, the number of poles is set by the number of magnets. So that's a huge difference. Because there is energy on the magnets, usually PN motors are more efficient than induction motors, especially at low loads. Let me now introduce you to a very exciting technology. Very long name, a permanent magnet synchronous axial flux motor topology. I'm going to refer to it as the PCB motor. One of the most radical changes that you see in this particular technology is the fact that the ion core from the stator is now gone. It has been replaced by a PCB. And in this PCB, the windings are copper edged. You can see it very clear on this picture on the right that will depict the windings edged into the PCB. Another change is the fact that this motor operates as an axial flux. Therefore, the flux will go from one rotor, right here, to a secondary rotor. So this motor is different from the two previous ones in a couple of different things. Number one, there's no iron core stator. And number two, there's two rotors. So the changes are both in the stator and also in the rotor. When you apply a three-phase inverter-driven power to this motor will rotate at a synchronous speed. So in essence, still a synchronous motor. Okay? Let me tell you some of the advantages of this particular motor. And I'm going to focus on efficiency, reliability, weight, and noise. From this picture, on the upper left side, you see the normal AC induction iron core stator or permanent magnet stator. The picture on the right shows the infinitum PCB stator. One thing is very, very important to say. This stator is only 5% of the weight of the stator on the left. Another thing to tell you, and you cannot probably tell from the picture, is that here you see the son of our CEO. It took us 2 bags of gummy bears to make him pick up this 18-pound stator. It took only 2 gummy bears to make him pick up this PCB stator. So there is a ratio between weight of a stator and gummy bears that it takes a kid to pick it up. So talk about efficiency. Number one, the core losses have disappeared. There is no iron. Number two, the amount of copper in this particular stator is about 66% less than what you'll find on a stator of a normal iron core induction motor. Therefore, your core losses are lower, actually zero. And number two, your copper losses are also diminished by 2 factors. The first one is less copper in here, 66% less. And the second one is the end turns. In normal iron core stator, the end turns are a major source of inefficiency. They don't do much for you. Also, let me talk about reliability. We talked about 6 different components to make this stator on the left, the iron core stator. What happens when the motors get hot and then when the motor cools down? Because these different materials on the stator have different coefficients of thermal expansion. When they heat up and when they cool off, they all return to the previous state at different speeds. This causes stresses between the materials. And eventually, 10, 12 years down the road, that stress will break the insulation, and inevitably, that stator will fail to a short circuit winding. However, on the PCB stator, there's only 2 main materials. One is copper, and the second one is FR4. These 2 materials have similar thermal coefficients of expansion, meaning that when the motor gets hot and when the motor cools off, there is very little stress between those 2 materials. So we have shown on their very high life reliability testing that this motor will last approximately 110 years, or about an order of magnitude. We talked about the weight. The stator is only 5% in general than the stator on a normal iron core motor for the same power. Last but not least, the PCB stator reduces noise at a very high degree. This motor is extremely quiet. We have tested the motor and have shown that under full load, full speed conditions, the dBA of sound power is only about 46, 1 meter away from the machine. What does that mean? It means that if we're looking for efficiency, you see this right line here of the PCB stator being higher efficiency than the current production and highest efficiency AC motor, and higher efficiency than the PN motor itself. That is specifically very well noticed at lower loads and lower speeds. So what does that mean? It means that the efficiency from electrical to shaft power, that is from wire to pump, has increased on a PCB stator because the losses have been eliminated. Higher efficiency brings a lot of benefits. Let's look at some of those benefits. Number one, you have a cooler operation. When the motor is running cooler, it's likely to have a longer life. A lot of different components have shown that for every 10 degrees centigrade that they see in higher temperature, their life will diminish by one half. That is true of insulation, at least. Okay. When you have a higher efficiency, you also have a lower power consumption. The lower power consumption will translate into reduced energy cost. And so your total cost of ownership will eventually pay off for the machines. And one last benefit of higher efficiency is that your maintenance costs will be reduced. You can sometimes skip cycles of maintenance because either O-rings, seals, and other components will not have seen the stress that most motors see under higher temperature. One more thing to point out is that the PCV motor is integrated to a VF drive. That means that motor and VFD are fully integrated and fully tuned to give you out the most optimal conditions of operation. There's other advances in motor technology that this PCV motor takes advantage of. For instance, the integrated VFD uses silicon carbide power transistors, which are more efficient even at higher frequencies. There's built-in sensors for temperature, for vibration, for voltage, for current monitoring. So all this is happening in real life. In other words, there's a great communication going on between the inverter and the motor. The inverter tells the motor what to do, and the motor tells the inverter how happy it is doing what the orders are. Also, there is control software, and this control software will help us give us all the insights of the motor performance, all at real time, so we can gather a number of analytics that will help us in optimizing the performance of the motor. Once we know the performance of the motor, we can configure the motor exactly for the application that we're looking for, be it higher torque, be it higher speed, be it a combination of both. Once we know exactly how the motor is doing, we can configure that drive and motor to operate exactly as we wish it to operate, the most optimal conditions. There's other advances that we see in motor technology, and we benefit from that. Computer and software engineering allows to make better programs to take into account what we learn from the field and all the analytics that we gather with the VFD. Therefore, we can make better programs, not just to design the motor, but also to make the motor operation more reliable and optimal. In addition, we have mechanical and electrical components that now can be automated. And that is a very, very good deal because it will lower the cost of the motor, allowing for automation to take place. Less mistakes will render high reliability. Last but not least, we have very smart dynamic test systems. Test systems are going to be telling us the things that we have to be watching for. When we're exceeding temperatures, when we're exceeding vibration, when we're exceeding currents, when we're seeing over voltages, when the load is acting in a way that shouldn't be acting. And all those things can be incorporated back into the computer and software engineering, applied into the automation points, and then move on to better and higher efficient designs. There are some new trends going on with motors and pumps. As we look at the integration of the drive and the motor themselves, we can also talk about the fact that there will be integration of drive, motor, and pump. And that is going to reduce the number of components. It's going to increase efficiency. It's going to allow us to refine the manufacturing techniques, and it's going to allow us to adopt new and advanced materials that might be better working and better performing at higher temperatures, that might be better working and performing at a cooler temperatures, and also that we can integrate into AI assisted design. Artificial intelligence is now here to stay, and we can make use of it to make us design better pump, motor, drive, integrated system to make it more efficient and to make them operate and adapt in more condition. I'd like to move into something very important. Efficiency is a huge deal. It allows us to conserve energy and is a must in every design. The drive to reduce environmental impact must continue to push for cleaner and better and friendlier motor systems and lower carbon footprint. We need to reduce the energy consumption. We need to optimize component lifespans. We need to increase the custom functionality of full system improvements. All these things are just to get to one point. We need to leave this earth much better than we found it. And we all have to do our part. We are doing our part at infinitum. I want you to look at this table here. And this table compares a normal 10 horsepower AC induction motor to a 10 horsepower PCB stator. When we compare the materials on both stators, we begin to see that there is a difference on the carbon footprint that each one of them will be bringing about. Altogether, we have shown that the carbon footprint is reduced by 18% with just one motor. Now, multiply that by millions. Keep in mind, the electric motors utilize about 50 to 55%, depending what part of the world you're in, of all the power generator in this world. So making motors more efficient contributes heavily to lower power consumption, and lower power consumption contributes heavily to reducing the CO2 carbon footprint of humans on this earth. This concludes my presentation. I will follow it with answering to some of the questions that came into the chat. I'd like you to please follow us on LinkedIn so you can stay up to date on the latest news and the upcoming webinars. With that, I thank you, and I will leave it open for the questions that might have come into the chat.
All right. Thank you, Ramon, for a great informative session. So we will now take the opportunity to answer any questions we can in this time. Again, to ask a question, type your questions via the questions icon located at the top right-hand corner of your GoToWebinar screen. So our first question we have here is, can this motor operate with any VFD?
Oh, good question. Uh, the answer is short no. And the main reason is that since the motor has no iron core, there is no inductance on which most of the normal VFDs are based. Therefore, the topology is very different. So no, the drive has to be an integrated motor drive that will take into account the fact that there's no iron in the stator.
All right, thank you. The next question is, what's the difference between the PCB and EC motors? Do EC motors have iron core rotors?
Yeah, the The AC motors have, like I said, either a laminated core or a solid yoke of steel. On a laminated core, usually the magnets are embedded, like the one we showed in the picture before. On the solid yoke, usually the magnets will go around the stator and called surface mount. So yeah, the rotor is an iron core stator. On a PCB, obviously, you have to have iron to back up the rotor. So that's similar in that sense.
And I would add to that, Ramon, like I think weight difference is substantial as well, because now I think we're removing a lot more material, like Ramon mentioned earlier. So there's will be some size and weight differences.
All right. The next question is, wouldn't the less windings in the PCB stator decrease the performance of the motor?
Not necessarily. And the reason is because of the way the copper is etched on the stator. It allows for current density to run on a flat surface, if you will. And so that current density on a PCB stator can be much higher than the amount of current that you can put into a normal winding. And I'll just give you this example. Think of a coil that has, say, 10 turns. There's going to be invariably one wire that is going to be on the center of that coil. That wire carries the same current as the other wires on that coil, but it's in the center. So for that heat to be extracted from that wire, it'll have to go from copper to enamel, to enamel, to copper, to enamel, to enamel, to copper, until he reaches the final frontier of enamel insulation. Then he has to go through the insulation between the wire and the iron core. Eventually hits the iron core and the heat will be extracted. The current density then on a normal stator winding has to be much lower than what we can put on the PCB stator.
All right. So the next question we have is, it sounds like permanent magnet motors are in general a superior motor technology. Are there any circumstances where an induction motor would be a better option over a permanent motor?
Yeah, there's always reasons why this technology has been around for 120 years and still widely used. There are some specific occasions where the induction motor is going to be slightly more efficient than the PN motor, particularly in very large machines. I'm talking hundreds of horsepower. At that point, the induction motor is reaching its peak efficiency, and a permanent magnet motor has some specific drawbacks because the speed cannot be reached, or because of the weight of the rotor, or the losses of the magnets are a bit too much. So the induction motor in that particular case could be slightly more efficient. In general, the case is that the permanent magnet is more efficient than the induction motor. And the main trick on that is the fact that the rotor has energy added to it, where in the induction motor, you don't have any, and the rotor itself.
The next question is there a way to bypass the integrated drive in the event of failure?
Is there a way to bypass the integrated drive end?
Drive in the event of failure.
No, there's a lot of safeguards built into the drive itself. Like I explained before, there is constant communication between the motor and the drive of the VFD. So the motor will always tell the VFD how well it's doing against the load conditions. And in some cases, we have safeguards where if the motor is seeing too high of a temperature, we will reduce the amount of current allowed into the motor as to make sure that we don't destroy the motor in the process. So there is a number of alarms. There's a number of steps that we can take before we go into complete failure. I hope that answers your question.
All right, there's another interesting question. How long do you think will take till you integrate AI to the pump and the motor?
I think it will happen very quickly. And again, look, it's taken me about 35 years to learn the little that I know. And I can put that into AI, and AI will do a much better job doing a webinar than I can in about 20 minutes. So it is definitely coming in. It's here to stay. But we don't have to forget that we are the owners of AI. So whatever we put in, we're going to get back to the efficiency that we put in.
Yeah, I would like to add to that. I think it's getting there's a lot of trends of in processes and trying to get AI built into our daily workflows and processes, and we are seeing it increase drastically in the last couple of years, and I think it's just going to increase and accelerate, I would say.
Things like
All right. The next question is, what ratings, sizes, and voltages are available now?
good. So the PCB stator, again, as I told you, is only about 6 years old. But the ratings right now are anywhere from 3 horsepower all the way up to 15 horsepower. And the sizes vary in diameters depending on what you're looking for in terms of load, in terms of torque, and in terms of speed. We are currently developing higher loads, 20, 25 horsepower, but more immediately, we're developing smaller motors with the same technology, down to a half a horsepower, 1 horsepower, 2 and 3 horsepower, all with the same topology. And those should be
Next,
available soon.
the next question is, do you need special bearings or any other special hardware for this motor?
Not necessarily. The bearings are the same as anybody uses in any motor and any shaft. Obviously, we have available seal bearings, uh, shielded bearings, ceramic bearings, hybrid bearings, steel bearings. All of those are available depending on what the customer requires for their application. But the hardware is pretty much the same as any other motor. The difference is the topology again. The difference is taking the weight out, taking the arc losses out, taking the copper losses down, reducing the noise, reducing the weight, and make a motor that's overall more efficient and friendlier.
Yeah, I would like to add as well that we're working with Infinitum to make sure like all the radial loads and axial loads are taken into consideration when sizing the motor and with the pump. So we're working together in making it to ensure that the standard bearings will fit into the pump and motor.
Thank you,
Thank
Nick.
you. So, next question is, which motor is more energy efficient comparing PCB motor and ECM?
The PC motor is more efficient, and specifically because there is no iron losses on the stator. I mean, just off the bat. And I think the curve that I showed you before shows there's slight increased efficiency at any point in the curve, either speed or torque or load.
Yeah, and I think I believe it's even better at part load, correct?
Correct.
Yes.
The next question is, if we want to upgrade to these motors, do we need a special controller?
Well, the controller is built into the VFD, and it will work with any other communications you might have. The VFD can take analog input, Modbus, BACnet, and other protocols, so we can hook up to your PLC system or whatever your system is going to be. We are able to communicate either way, and you can send your command in any different way you might have it.
So, are special filtering line or load required or difference between the two motors? Are the electrical noise issue different?
Uh, I think it's a very, very good question. Electrical noise is just corresponding to frequency and load. So there is a total harmonic distortion that is going to be on any motor that is operated by a VFD and it comes out of the grid. So the differences are very little. But it's a good point that you bring up because we have developed a active uh, filter that we are going to be putting on motors in the very near future to eliminate any harmonics and any total harmonic distortion, bringing it down to single digits.
The next question is, if the control board fails on a DE pump, is there a bypass to still operate the pump, or are you out of commission?
I think you can do it both ways, but it's tricky. So I'm going to leave that question, and if you can email it to me, I will talk to the folks in the electronic side and give you the answer correctly. I don't want to mislead you in this, but there's a way to bypass that.
Right. The next question is, can you explain motor efficiencies and how they are tested at the factory with a shop curve and how this test is done?
Very good. So at the factory, and especially in the R&D lab, we have a huge array of dynamometers. These dynamometers are connected to computers that will run automatic tests, and they can be remotely controlled. These computers and these programs that we have into the dynamometers are capable of testing all the parameters of the motor, not just speed, not just torque, not just current and voltage, but also we will measure temperature, total harmonic distortion, and efficiencies at any point that we want to measure. So we can break down the efficiency of the VFD, the efficiency of the motor, and the complete efficiency of the system. So it's a fairly sophisticated test system that we have in place. And we do it for many torque values, so we can use torque heads that are specifically measuring the torque where they're most accurately.
Right. The next question is, how does the cost of PCB motors compare to the cost of permanent magnet motors?
We are competitive, so it relates the same. And don't forget one thing: the PCB is manufactured under manufacturing techniques that are very widely available. Nowadays, we all carry our PCBs with us, right? Meaning that PCBs are made in the millions upon millions per day, and we make advantage or take advantage of that particular manufacturing technique. I challenge you to see if you're carrying an iron core stator in your pocket today. Definitely you're not. But a PCB, we carry a bunch of them all the time. So in that, using those manufacturing techniques, we're able to take advantage of the cost reduced by the automation and by the widely available flexible manufacturing techniques on PC boards.
The next question is, for motors that typically run at full speed, adding a VFD could have a negative impact, like 3%, on energy efficiency. Do drives typically switch to line power when running at 100% speed to avoid this penalty?
Well, the thing is that uh, if you're going to be using a VFD, likely you're going to be using variable speeds, right? If you're going to put a VFD for a motor, you're going to be running a full speed. I think you're wasting your money. Now, if I understand your question correctly, is can you bypass the losses of VFD when it's running at full speed? At full speed, the motor is running usually at the highest efficiency point. So the VFD is going to be running also at a very high efficiency point. There is a small penalty, but very small. Now you have the advantage, however, that you can run the motor efficiently at a bunch of different load points in different speed points, right? So allows you to, yeah, you might pay a tiny penalty for running the motor at full speed with a VFD, but you have it into your hand, you have it into your availability to move the motor to different load points, different speeds, and be equally efficient as you were at full load.
Right. The next question is, does the PCB technology can be applied to fans and blowers as well?
I'm sorry, can the PCB technology be?
Applied to fans and blowers as well?
Absolutely. I think I showed a picture in the presentation, but Right now, Infinitum has an installed base of about 40 to 50,000 units, and most of them are cooling data centers, so blowing air. So the technology can be moved to air, can be moved to liquids, and can be moved to non-compressible solid materials like gears and material handling applications.
Right. The next question is, what's the largest motor horsepower available with the PCB motor design?
At this particular time, our largest production is 15 horsepower. And like I said, we're moving quickly into larger rating motors for the motor, anywhere from 20 to 25 horsepower.
The next question is, why are PCBs not more widely used in HVACR right now?
Because the technology is new. But if you have an application, let us know. We want to make it more widely used right now. Again, we have found a very, very sweet spot moving air because the motor is very quiet, it's very efficient. And for instance, in data centers, which are utilizing about 10% of all the energy produced in this country, they are under a magnifying glass, they're under a spotlight, so they are always looking for an efficiency that is going to be brought about by new technologies. And so we enjoy that field right now very, very much. But we also provide many, many solutions to HVAC. We move air very easily. So if you have an application, let us know. We want to be more widely acceptable. We don't want to wait 120 years to be the number one installed base of motors out in the world.
Yeah, I would say we will need to do more talks with engineers and getting them comfortable with the technology. Ramon mentioned it's a very new, very I would say in the last 10 years we developed it, and I think there's a lot of benefits to it. Uh, just getting the name out there, all the benefits like on sustainability, like reduce embodied carbon and operational carbon as well. That's the biggest factor with this technology. So I think we just need to go out there and explain it and finding the right applications for those motors.
Thank you, Nick.
So, can you quantify the heat dissipated by the motors? Can it be calculated as a function of the motor HP?
Absolutely. Efficiency is the opposite of losses, right? So you have power input and power output, and in between, there is losses. Efficiency is calculated by dividing the power output, that is mechanical output power, divided by the power input, that's electrical input power. The difference between the two of them is the number of watts that are being lost in the system between the drive and the motor. So there's an equation very easily, right? So your total power input is equals to power output plus losses. If you know your power output, you know your power input, you can calculate your losses at a numerical value.
The next question is, what is the expected lifespan for a PCB motor?
Excellent question. We have tested it, and we have third-party labs tested, and we think it's in the order of 100 to 120 years. So right now, we are saying it's 110 years.
All right. So the next question is, can the PCB motor run on a standard three-pole contactor?
Yeah, as long as we use the drive.
Hmm. Can they be can they be used in a classified area? Example, class 1 zone or class 2.
Uh, Not at this point, but it's something that we're working on right now. If the applications are of enough volume for us to put the investment into it, we'll be more than happy to. I mean, we're not sparking anywhere, and so we can make it class two, and I don't know if we're going to be eventually being class one.
The next question is which Armstrong pump models are using the PCB motors right now?
Nick?
I think you're on mute, Nick.
So sorry. Yes, we're still working with Infinitum. We're still working on the details, but right now we're still looking at which motor technology we're going to be using on which motors. But there will be on most of on we want to have it on most of the VILs, vertical inlines, and tangos. But we're still working on the ranges and sizes at this point.
The next question is how is the motor cooled? Is there any limitations to work in wet environment? Outdoors, like very cold or very hot environment?
Excellent question. So the motors, um, can you hear me?
Yes.
Yes.
Thank you. So the motors are rated at IP65, right? That's the ingress protection rating. The motor is also rated to operate at full load at 40 degrees C. Up from 40 degrees C, we'll have to have a derating calculation. On the lower temperatures, we go down to minus 20, right? And the main thing is that the grease on the bearings themselves, like any other motor, operates only within certain temperatures, right? So if you're going to have an application that is an extreme low temperature, an extreme high temperature, we have to work with a bearing manufacturer to pack the bearings with a very, very specific grease in such a way that we're going to be able to operate on the low side and operate on the high side. How is the heat extracted from the motor? That's one out of 92 patents, 40 of which are still pending. So I'm not going to tell you exactly how we extract the heat, but let it suffice that the motor operates very well in conditions that most motors operate into.
The next question is are these motors designed on the same frame basis as original motors?
In some cases, yes. I mean, we have a C-phase mounting, but because of the shape, the form factor of the motor being more of a pancake than a sausage, they don't have exactly the same NEMA mountings that you're going to find, right? So we still have the C phase and we can have the shafts to meet NEMA 1 conditions. But obviously, being that we are a disc, is not going to comply with a lot of the NEMA specifications in terms of length and diameter of the motor. But the mounting can be made such that it can be a C phase.
Next question is how long does the grounding brush last? Does it require service at some point?
Another excellent question. We use a carbon brush that touches the shaft at all times. The brush is made by a company in Milwaukee called Hellwig, so it's very widely used. And we have done our own testing, and we calculate the life of the brush to be approximately 10 to 12 years. So I don't see that as something that has to be replaced. I think there's other components in the motor that are going to last slightly less.
Right. The next question is are these motors available as standalone, not integrated with a pump for use with fans, compressors, and etc.?
Yes, mainly for fans. They are all available, right? Again, like I said before, right now we're moving air because that's the easiest fluid to move. Then we're moving to pumps, and then we also have moved into material handling. So the application as any other motor. In fact, we also have developed a 240 kilowatt motor that is used for vehicle traction. So it's available for the application. The only thing different is the topology, the different form factor, and the fact that we're more efficient.
Do the PCB motors conform to motor size and mounting configuration standards, or are they so different that they create new shape factors?
You know, the shape factors are different. Like I explained before, they don't comply with full NEMA 1, right? They comply with having a C phase and shaft specifications to whatever your application requires. They are obviously pancakes versus sausages, if I can use breakfast terms in here. So no, they They fit into most of the application, but not necessarily are going to be a one-to-one replacement to an induction motor or to a PN motor due to the form factor being different.
The next question is, does the PCB motor have any advantage or disadvantage when operating under voltage? This is voltage sag. Typically, motors operating near below rated voltage will experience higher current draws, lower torque, and longer start times, resulting in reduced starting ability, lower load capacity, more overheating, and a shorter motor life.
Very, very good question and excellent point. We work on voltages that are the rated voltage, say 460 volts plus or minus 10%. And there's also a minimum voltage under which we can operate. And that is based on the fact that the motor, since it has magnets, it produces a back EMF. So at the DC link of the inverter, we need to have enough voltage to overcome that back EMF, just like any other motor. So you might have an under voltage and we'll still operate okay. We need to have a certain amount of voltage in order to have a DC link that will operate beyond the back EMF of the motor. So no difference from a normal PN motor, if you will.
The next question is, how do you adjust the speed of the motor? Or is it a constant flow application?
Now, the speed of the motor can be controlled by the VFD, and you have different HMI ways of getting into it. So your machine interface with the motor can be from a computer, it can be from an iPhone, it can be from a laptop, it can be from an iPad, you name it. So there's, as long as you can communicate with the motor, you can control the speeding any way you want. And also, we have specific uh, mechanisms that you can use on a program where you can set the speed of the motor, right? And so you can tell it to operate a certain speed, and the motor will operate fully efficiently to that. So the control is that, like with any other mechanism, talking to the VFD, and the VFD controls the frequency, which controls the speed of the shaft.
Yeah, I just wanted to add, Ramon. So yeah, like it would be using a speed signal, either analog or digital, to control, so either from differential pressure or single point. That's the one way of controlling the pump with this technology.
Right. The next question is, are these PCV motors being built in North America?
Yes, they're built in our factory in Mexico, in Saltillo, Mexico. We have one factory, 62,000 square feet, that came into functioning in May, and we just began breaking ground on a second twin factory right next door with another 65,000 square feet. So it's all designed, uh, built, and produced in North America.
The next question is, when will PCB motors be available with Armstrong pumps?
So I was just saying earlier, we're still working in the details. No dates as of now, but we're looking to have it at least for next year. Hopefully, if all the details works out. It's a joint collaboration, and Armstrong has been a leader in innovations, and we want to look at every motor technology out there that can help the customer out on their specific applications. And it seems like Infinitum is a great partner for this initiative.
All right. Next question is, in cost-wise, how much percentage is the difference between using iron core and PCB?
So it's competitive. Overall, there are things that cost less, and there are things that cost a bit more. But overall, we are fully competitive with the motor and the FD combination.
Are there any applications where a PC motor is not appropriate?
I think we talked about uh, explosion proof. Right now, it's not appropriate because we don't have it, but there's no limitations to the technology itself. So places where it's outgassing, like in outer space right now, we haven't tested it for that particular application. Uh, we haven't tested the motor at altitudes more than 40,000 feet. Uh, so for mainly all the applications that you see uh, on nominal application where an induction motor is being used or a PM motor is being used, we are equally useful, except a bit more efficient and lower weight.
Yeah, I would like to add also, Ramon. I don't believe those are rated for outdoor application. Um, I believe that because of so those motors would be only be used indoor at this point.
Yeah, right now the rating is IP65, so there's a certain amount of water jets pressure that we can take, and certain size of particles that we won't allow in.
Right. The next question is, what is the maximum operating temperature for these motors, or
Right
maximum
now,
internal temperature?
we rate the motors at minus 20 C to 40 degrees C, and on both sides, below 20 degrees, consult the factory for a D rating, and above 40 degrees, consult the factory for a D rating. So the motors can operate at higher and lower temperatures than we specify, but there's always things that we have to take into consideration.
Could you share the highest power available for the PCB starter motor?
Right now it's 15 horsepower. We're working on 20 and 25 at a later point, and we're also working on lower ratings, 3, 2, 1, and fraction horsepower. And the smaller ones are going to be available second quarter of next year.
Will your motors use wedge coils or spiral coils?
uh, they are a distributor winding, except it's edged on a PC board. So if you look at the stator, like in the picture I showed in there, if you put it under the light, you can actually see the windings on a distributor way. They are phased out 120 degrees, just like they will be on a normal iron core stator, except this case is axial flux instead of radial flux.
Do they work on single phase voltages?
Not at this point. We had to develop a VFD drive for single phase, and we yet have not seen the the necessity to do that because the application on VFDs for single phase and low voltage haven't really been that high for us.
I think this may be the last question, but if there are any more questions, still I'll put them through and we'll get back to you guys. The next question is, we typically tell a customer that the minimum speed of a pump is dictated by the minimum speed of the motor, approximately 25% of max speed. The motor requires a minimum speed to provide the required amount of airflow to keep the motor cool. Since the PCB motor runs cooler, does that mean the PCB motors can run to slower speeds as compared to PMM motors?
Excellent point and excellent question. I appreciate it. Yeah, we can go down to maybe 50% of maximum speed and still have enough airflow from the impeller to cool off the motor. So that is a big point for our motors. The way we rate them, and because the efficiency is a very flat curve, we can take the motors down to say 50% of rated and still operate.
Great. Thank you. I see there are still so many questions there. So if you were not able to get to your questions, don't worry. One of our team members will reach out to you. Now I will hand it over to Ramon and Nick for final remarks.
So thank you everybody again. I know you spent an hour with us. I hope it was worth it to you. If there's questions that we couldn't get back to, I'll receive them. I'll talk to the right experts, and I promise you we'll get you an answer. If we don't get you an answer because we don't know it, then we're going to invite you to be the next presenter on part number 3 of this webinar. Please don't forget to follow us on LinkedIn, goingfinited.com.
Nick, final remarks?
Thanks for attending the webinar, guys. I hope it was very helpful. So looking forward for more questions and stay tuned for maybe a part 3 of this webinar. maybe focus more on the VFD. I know there's a lot of VFD questions, so we're probably going to work on this with Ramon, and stay tuned.
Right. Thank you, Ramon and Nick, for a great webinar, and thank you all for joining. If you want to stay in the loop with all the latest updates, make sure to follow us on social media. We love sharing sneak peeks of our webinars, cool case studies, and a lot of other interesting content. So if you haven't already, come join our online community. And don't forget to scan the QR code you see on your screen right now to register for our webinars. As mentioned before, be sure to follow us on social media as we will share the sneak peeks over the next few weeks. And in the next few days, you will receive an email from Armstrong Communication with a PDH certificate and in a separate email, a recording of the webinar. To learn more about our solutions, please visit armstrongfluidtechnology.com. Thank you for your time today, and please spend a few minutes on the survey you'll receive as you exit the webinar. We'll see you soon at our next webinar. Thank you.